First of all, let's talk about the scope and syllabus of this course titled Foundation of Scientific Computing. This is offered as a science selective course to our third year and final year undergraduate students. No specific prerequisite is necessary for this course other than exposure to courses which are given to our first and second year students on calculus, ordinary differential equations and partial differential equations. Students at IIT Kanpur usually take an introductory course on computing, which is however not related to scientific computing, the subject of this lecture series. However, I must emphasize that any new material that will be taught in this course will be done so very thoroughly, and for that there is absolutely no need for any book or monographs. Now, going to the details of the syllabus for this course, we'll begin by talking about basics of computing, and thereby we'll talk about discretization of governing equations and associated numerical errors. As usual, we'll start with computations of ordinary differential equations. And since some of the students may be familiar with it, we'll introduce what is known as stiff differential equation. These are a very important class of problems and they need to be handled with care because this depends on parasitic error growth, and solving stiff equation is performed via various routes. Here we'll just briefly mention about orthogonalization, but spend a little more time on a new method which has come up over the last 30 years or so. It's called the compound matrix method. Once we are through with this, we'll also talk about various two-time level methods of non-stiff ordinary differential equation, and then we'll move on to classification of governing partial differential equations that one encounters in scientific computing. We'll see that these equations are classified into parabolic, elliptic and hyperbolic equation. And one of the interesting aspects of scientific computing is, irrespective of whatever class of equations we solve, we we computationally handle it as if we are treating the problem as parabolic or hyperbolic equation. And in that respect, wave mechanics is a very important issue that we should be talking about. Two types of waves that one comes across. One, those are governed by hyperbolic partial differential equations, and the other one is called the dispersive waves, which are governed by anything other than hyperbolic PDEs. And all these waves are basically governed by dispersion relation. That actually, in a sense, mean how space and time variation is governed by these equations. So this is an important concept. So we talk about wave mechanics in quite a bit of details. Next, we'll move on to finite difference methods, talking about discretization of spatial derivatives via polynomial expansions or by operator notations. In this regard, we'll be talking about explicit central methods as well as upwind methods. Once having done that, we'll systematically go over discussing about parabolic differential equations. And in this topic itself, we'll introduce explicit and implicit method of solving differential equations. Once this is done, we'll move on to elliptic PDEs, and in this methods we basically talk about the classical iterative methods, which will actually, in a sense, treat this elliptic partial differential equation in a parabolic framework. So we are in that sequence coming along. We'll also talk about what is known as alternating direction implicit method or ADI method. This was quite popular about 40-50 years ago. Now it has been overtaken by other methods, and one of the newer method will include in this course is called the multigrid method. This is a huge area of research which can actually cover a full course itself, but we'll just simply introduce the scientific aspect of multigrid methods. Having solved the parabolic and elliptic PDEs, we'll naturally move over to hyperbolic PDEs, and while doing so we actually introduce a spectral theory of discrete computing, because many of the ideas of computing has evolved while performing stability analysis of partial parabolic PDEs, but essentially the error is governed by methods or equations which propagate the error as waves. That's why we emphasize quite a bit of our time on wave mechanics, and while talking about the stability analysis we'll specifically talk about theory of signal and error propagation, and once again we'll talk about dispersion relation preservation property. Thereby we want to highlight that the space-time dependence of exact differential equation and numerical methods must be close to each other. That's what is meant by DRP property. Now in this context, in solving hyperbolic PDEs, we'll be talking about convection equations, one-dimensional convection equations, and we'll also talk about refraction or diffractions of mechanical waves. This will talk about with respect to surface gravity waves that one sees in the treatment of water waves by linearizing and treating it as a inviscid flow property. Subsequently, we talk about how these surface gravity waves are affected by dissipation and nonlinearity. In that context, we'll be introducing the students to soliton and a special class of periodic waves called sinusoidal waves. And having done that, we are in a framework where we can talk about how to design high accuracy, high fidelity computing methods. That would involve severe control of errors, and this we can pose itself as an optimization issue. And in this context, we'll talk about near spectral compact difference methods, and which will occupy quite a bit of our discussion space. Now, while talking about the spectral analysis, we'll introduce the effect of nonlinearity in computing. That brings about aliasing problem and also focusing of error. We are already maybe familiar with the effect of nonlinearity in compressible flows where discontinuities come about in terms of shock waves and associated Gibbs phenomena. Here we would like to talk about one particular topic which is very specific to computing. This is called the spurious propagating waves, which are called the Q waves. This is what we will be talking about. Having exhausted various topics of finite difference method, we will move over to finite volume and finite element method and systematically compare these methods with finite difference methods. And we'll basically keep our attention focused to propagation problems, because that's what is important in scientific computing. I think this will more or less finish all the available time that we have over the semester, and we would like to basically give you some information about textbook and references. For this course, what we are going to do is we are going to record the live lectures given to the students here for this course on Foundation of Scientific Computing. It's a science elective, so it's not necessarily a compulsory course. Those who are interested, they opt for it. And most of the material can be found in the following references. Number one is a book that was written some time ago by me, but although it's not really up to date. Good news is that all the chapters of this books are available in Google Books for free. So there is very little effort one has to pay in downloading these materials. And also, of course, all the slides that I'm going to show it to you during the teaching should be made available to the students of this course. I would also like to point out that there is this book on fluid mechanics by Professor Kundu and Cohen. There is a paperback Indian edition available now, and if anyone is particularly interested in reading materials on waves, this is an excellent book. I would wholeheartedly recommend this. Well, warm welcome to all of you. Beginning of the semester, I suppose there's a first class. So we have assembled here to talk about foundation of scientific computing. Course number is SC 371. Okay, that's me. You could look at me here, and this is the way to contact me anytime you need to. Those are my couple of email IDs. You can call me on internal numbers on 7945 or 7253. There are no fixed contact hours. You can just simply call me and drop in. Since I will be busy teaching a couple of courses in the morning half, so it would be preferable that you look for me in the afternoon. Don't bother about this URL, but for the next one you should please make a note of it. This is a course URL we have set up on a server called spectral.iitk.ac.in. We will load some material from time to time on this for a short while. I don't wish to keep it permanently, maybe for a week or so, and then we will download it. Okay. As far as the grading and exams are concerned, it is fairly straightforward. Will depend mostly on your midsem and endsem. That should account for 80% of all your total grade. We will of course do some projects or that should take care of the two. Now, of course, when we talk about a subject like this, scientific computing, well, nothing could be said more eloquently by what Mark Twain has said, that fascination with science always yields some dividend, and one could come out with a fantastic amount of returns. Let me also tell you, scientific computing is not the type of computing we talk about that you do using a commercial software bought in the marketplace. To take the analogy to extreme, it is almost like comparing astrology with astrophysics, right. So, it is the same thing here. Scientific computing is distinctly different from so called engineering computing that you do buy from those software in the market. So, that is why let us probe a little bit more about relationship between computing and science. I just quoted this paper from Nature, appeared a few years ago, talking about what would be the state of art as far as computing is concerned in year 2020. I don't know why people get this fascination for 2020. Everybody writes about 2020. Probably it's something to do with short-sightedness. People want to keep that way. Well, let's look at it how science is improving. Science is becoming less reductionist. What exactly we mean by that? You know, this is that cause-effect model that we usually talk about, that we have a definitive cause, we see an effect. That is your reductionist approach. However, we see all kinds of systems around ourselves which are far too complex. To model those complex systems, we need to have a different approach, that is what we call as an integrative approach or inductive approach. So, that means that we are just no more content in visualizing systems by constructing abstract models, simple models, paradigms, concepts. What we instead like to do is bring in the complexity of a real life system, and that is what we talk about when we say we are going from reductionist to integrative. So, in that particular aspect, this statement is very cogent here, that if we look at
what we are going to do with applied computer science, we should play the same role that the mathematicians were playing for 2-3 centuries, basically providing an orderly formal framework that should help us explore newer avenues for understanding science. So, we are just taking it to a next higher level. What theoretical tools cannot deliver, we aim to deliver some of them using computing. So, basically then we will go from models to actual dynamical systems, and when we are talking about a dynamical systems, most of you are familiar. You have a transfer function that characterizes the dynamical system. You have input and then you get definitive output. The only thing is, this dynamical system is not as simple as what you may have done in your basic electrical engineering courses. It is going to be lot more complicated, because the main dynamical system by itself may consist of many subsystems. The input also could be multiple. Think of a very simple example. For example, when we toss a coin, it is such a simple event, right? Even today we cannot model it because of multiple inputs, and because probably the model that we try to look at is not rooted to a simple system that we are used to seeing in a mechanical system governed by Newtonian law. So, what happens is, basically that is why we resort to statistical tool, right. So, we cannot model the system. So, if we cannot do that, we incur some error. When our model itself is faulty, we call such error as the process noise. So, we do not even know enough about the process itself. Then of course, you have the problem of modeling the input, and finally, even the measurement of output. Measurement noise also plays a major role. So, when we take care of all of that, we actually go to our integral dynamical system approach. In the context of present day, what we can do is we can fall back upon calculations which have to be very high fidelity calculations, and we should draw tools from advancement arising in hardware, those arising from software. We could come out with better algorithms to solve the actual problem, and all of this should also be supplemented with improvement of our theoretical model itself, right. So, in the ideal scenario, a computational scientist should know the principles, the way the information is handled inside a computer, because that is rather important, because you are looking for advancement. You should know how this data are put in, how they are handled, and moreover one should also know the scope of limitation of the simulation itself. We have a general tendency to treat this as a black box system. So, we tend to shy away from knowing the nuts and bolts of what constitute those modeling tools. That should not do. If you are going to contribute significantly meaningfully, it is quite likely that you need to really know how this whole black box is working, so that you can yourself contribute to its improvement. So, that means actually to know how to write large codes and how we test them in a modular manner. These are not like your operating system you buy, they keep on adding patch over patch, and today whatever the operating system you have, if you try to put it in a computer of 10 years ago, memory will not be sufficient, right, because that is a very faulty model of developing even the operating system that we are saddled with. Now, drawing the analogy again, the computational expert should view themselves as mathematicians, like the way that we see them functioning in different branches of science. At the same time, The theoretical scientists also should be conversant with computational techniques, because then only they would be able to meaningfully contribute, and this synergy will of course take us to greater heights. So, we basically need scientists trained in this advanced methodologies, and with the challenging problems that we find out in science, that should help us focusing and motivating our research in computing. You have seen some such benefit already accruing in the field of sensor network, data mining, data integration, grid computing, cloud computing. You have a whole host of new branches coming up. Well, these are some of the things you can see where scientific computing can go, all the way from atmospheric science, which has a very definitive history of its development, to new subjects like genomics, which are probably only 20 years old, 30 years old. And we have said that in real life situation, integrative system level approach will be sought, and these are already being seen enacted in fields like biology, climate, ecology, earthquake prediction. They all essentially depend upon large computing resources which are distributed in nature. We will talk about distributed computing, a brief introduction of it. And this is one prediction, that in year 2020 we should be looking at complex ecosystems with millions or even billions of computers, which will be called tiny modes or nodes or pods. They would be deployed to track a complex systems. However, having said all this inspirational talk of what we should be doing, what we are doing currently also leaves us some room to probe further, and I am not talking about conspiracy theory. This is what George Orwell said, that within any important issue there are many more other issues which people are reluctant to talk about. So, we will be talking about some of those issues and find out what is a better way of computing, and we will set the thing. Now, this is a lighter aspect of computing. We all see from time to time there is a intense competition among diverse groups, saying that what they can do with computing, and they generally use the word supercomputing. We never made out what really supercomputing is, because these are the kind of diverse activities those have been claimed. For example, people talk about aerodynamics of Pringles, and this is taken from a CNN site which talks about Pringle potato chips. The story is, it is not really a potato chips. How many of you know that? It is all synthetic savory, it is all industrial product. If you look closely, look at the content, you will find out that it contains less than 50% of potato flour, rest of it are different types of ingredients. So, it is really not a potato chips, but then people are making a big hoo-ha about it on a popular TV program, saying that we need to know the aerodynamic features of these chips, because they are going in a conveyor belt. We do not want them to fly off. Such a noble goal, huh? Well, on the other extreme, people have been looking at some real esoteric activities like creating a computer playing, the chess playing computer. This began way back in 1956. I will give you a little bit of a milestone shortly, and it took 41 years when a computer was really able to defeat a grandmaster. So, Garry Kasparov will be remembered among all the grandmasters for this dubious distinction. So, this is how it all began in 1946. First computer was called ENIAC, Electronic Numerical Integrator and Computer. And what was it doing at that time? Of course, war has ended, but the preparation never ceases about fighting war. We always like war, right? So, people are looking at application in ballistics. Then of course, better wind tunnels to design deadlier aircrafts or maybe even benign peaceful uses. Then this is one thing that we always give credit to, this group of people who have been trying to do almost an impossible job, that is weather prediction. So, they were trying to do a better weather prediction and look at their success rate. To predict 24 hours of weather, they had to run the code for 24 hours. So, it is a concurrent information processing, right. So, you look at the output and look out of the window and see what is happening. Are you calculating it proper? That is a joke, because weather prediction we are talking about is in a global scale, and looking out of the window is a micrometeorology that is done in a different context. I do not think people were that interested in micrometeorology in 1946, they were looking at the global weather prediction. And of course, our favorite is random number studies, and you may be interested to know that this is to consume quite a bit of power, almost well, you can see it is 160 kilowatt, right. Where is it? Well, it is written 174 kilowatt, and so that is to attract a lot of insects from outside. This was housed in a big room. The footprint of the machine itself is 80 by 3, and those are made from those vacuum tubes, used to generate a lot of heat, and those bugs, insects used to be attracted. They used to come and sit on them, they will die, and sooner or later the vacuum tube will give up, and then they will say we have a bug problem. And even today when we write a program and we get into some kind of trouble, we say we have a bug. So, that is the origin, it all originated there. So, we as we say that we still look at them as a bug even in the software, but at that time it was talked about in the context of a hardware, failure of a hardware. University of Pennsylvania graduate students actually have developed the same functionality on a chip now, which has a size of 40 millimeter square, and you can see the comparison here side by side, and it has power consumption has come down to 0.5 watt now, because it does not have those vacuum tubes, it does not have those resistors and capacitors, and of course, the size is really miniaturized. So, that is how we all began. Then in 1951, Professor Minsky built this computer to mimic networks of neurons in the brain called SNARC. This is a momentous day. Backus and his team at IBM started developing the scientific programming language called Fortran. I will talk about Fortran and other language in a little while, but please do understand what Fortran started with, it continues to deliver despite all the fashion statements that we hear from different language from time to time. It is the surviving scientific language tool. This was what I told you, 1957, the first chess playing computer MANIAC was designed at Los Alamos, and of course, in 1997 we know it finally came to the goal of defeating a grandmaster. So, this was the original startup point of chess playing computer, and this is where it all shown up its potential. We will talk about this aspect in a short while. Now, when we come to the actual usage of this high performance computing that came about, one of the nice milestone was achieved in 1969, when a general circulation model for coupled ocean and atmosphere code was run by Manabe and Bryan, and this significantly improved weather prediction. Needless to say that this was helped because at the same time, I suppose our satellite technology was also improving, and as I told you about integrative approach, weather prediction is one such integrative approach. because anything and everything that we can get from the atmosphere, we try to put in those information in our weather prediction code, and those all came around the same time. Our computing ability became better. Then we have all this other inputs coming from different technical sources that really significantly improved weather prediction. In a temperate climate like in Europe or in North America above latitude of 30° north, the weather prediction has really improved significantly. Now I suppose people can get very good quality weather prediction for 48 hours upfront. This is with the qualifier that even today also the same set of people will not be able to track a cyclone very clearly. Those are problems of fluid mechanics. If we have time, we will talk about them. But general day to day weather prediction with some weather events occurring, those could be done, are done quite routinely now. Well, 1972 was the time handheld calculator made its appearance, and it took only 4 years before Seymour Cray launched the first supercomputer. Now, I will give you a formal definition of supercomputer. You would be very interested to know that what that supercomputer delivered in 1976. I think all this laptop will beat that supercomputer hollow in terms of computing power. So, supercomputer is a euphemism. It is a fashion statement dependent on the time frame we are looking at. So, we have now more computing power at our desk than this supercomputer delivered. In fact, Cray 2 was delivered in 1986, and it gave us a computing power which is referred to by a first gigaflop machine. All your laptop and desktop PCs today give more than a gigaflop. So, you can see that that much of computing power you have. Well, it depends on us how we use them. So, are we using them as a supercomputer or a chat network? That depends on us. Now, one of the major aspect of supercomputing in science depends on how we solve the problem, and one of the algorithmic development came about with the advent of parallel processing. So, you are basically solving a chunk of integral problem in parallel by slicing it into bits, and your computer is going to work on them bit by bit and integrate the result, then you go to the next step, and so on and so forth. So, that is the parallel machine. That was the concept of parallel processing came about with the advent of connection machine. The CM machines came, and that also revolutionized scientific computing. Of course, this is what we all depend on now. The World Wide Web was developed by this physicist Berners-Lee. He thought he could synchronize the computing power at different part of the world and solve those big problems of physics. And we know how World Wide Web is used today. People are still not solving those physics problems for which it was actually thought would be used. The next milestone came about in 1997, where again we see a 1000-fold increase in computing power from gigaflop to a teraflop machine achieved by ASCII red machine. And to cut the story short, when we look at 2008, this is the fastest supercomputer available once again at Los Alamos. When it was introduced in 2008, it had 1.026 petaflops. How do we benchmark these speeds? They are basically done taking a set of linear algebraic equation available in this package called LinPack, and in this activity they actually were solving 2 million coupled equations simultaneously. That is a moderate number, not a big deal. I mean, we ought to be ready to do that any point in time in solving big problems. What was more interesting about this Roadrunner was that it is one of the most energy efficient computer. For each watt spent, it delivers 488 megaflop power. You probably know this existence of this list called top 500. You can go to the web and you can find out every year. I think in the month of June and November they update the list. So, the list that I am showing you is up to date. I think it has crossed 1.05 now. So, it is a marginal improvement over last 6 months. It is probably because of addition of more processors, but we are still hovering around 1 petaflop rating. This is the number 2. This is really fancy, isn't it? This is a Cray computer, Jaguar. This is at the Oak Ridge. This also comes close second. Let me tell you that all the top 500 machines that we see deliver quite a bit of process power, and these are the top 5 that you can see. This is the Roadrunner, this is the Jaguar, this is a new kid in the block. It just made its announcement last month, German group, but you can see the number of processors they are using. Of course, we do not call them any more processors, what we call them as cores, because each processor can have CPUs with multiple cores. Like most of you probably would be using a core 2 duo or dual core or quad core machines. This one actually uses a 9-core machine, 9-core processors. And you would be interested to know that this was actually developed for PlayStation by Sony. These are graphics processors. So, graphics processors have a enhanced ability for number crunching. So, they are very fast. So, in case any of you fancy to put up a fast computer together, the basic unit should actually be drawn from this graphics processor. You can actually see different machines uses different core. This has come about to about, well, crossed a petaflop barely, but using about almost 300,000 processors. These are the top 5 that you see in that top 500 list. Let me also tell you that do not pay too much of attention on this kind of listings, because there are lots of people, lots of organizations who do not want to divulge what they are doing, especially the defense research in USA will never compete for this. So, that is why do not pay too much of faith in this list. Although in India we are used to newspaper headlines that we are number 5 or number 18 now, those are not so good, but there are certain good aspects even for those activities. I am not belittling them, they are good, but let us keep that aside. So, that is what now you would have, that you want to solve a real time problem with a faster machine, more powerful machines. So, it connotes a powerful and expensive system. So, all these machines cost more than $100 million, and of course, they are used for weather prediction. We use it quite often, aerospace engineers, even for designing new cars, for looking at its crashworthiness or safety aspects. Such activities are taken, and of course, any problem on physics and maths which require large scale computing would use the best in the market. So, apart from those benchmark numbers, let us see what really distinguishes this high performance computing machines from the other machines used for non high performance computing. It all began with the idea of Seymour Cray, where he actually conceived of having a vector computer. So, if you have an unknown array, you break it down into few vectors and process them as vectors, and that is how this all began in that 1976 machine. Right now, we can go to not necessarily a vector, we have machines which uses very large number of interconnected processors, and these processors need not necessarily be homogeneous, means they need not belong to the same class or category, they could be heterogeneous. So, you could have a room filled with different types of PC and you can put them together in a cluster and you can derive enhanced power, which all originated in vector processing, and the current activity is what we call as parallel computing. Okay. So, with this definition of high performance computing, we can also see that there are other ways which we talk about. You may have heard of quantum computers, but let me warn you, quantum computers and the traditional computers that we talk about, they are apples and oranges. They do not perform the same task, they are not even fruits. So, even apples and oranges is being charitable to quantum computing. They actually solve entirely different class of problems. What you do with the classical computers, I do not think any quantum computer will be able to do it right now. Then you may have heard of grid computing, that is probably what World Wide Web was conceived of. So, now that is being exploited. Grid computers, then we know supercomputers, we have the mainframes, we have the minis, micros, then of course, we have the front end, the terminals, and we may have embedded computers that should come in most probably in near future in all white goods, domestic purpose usage. Your fridge, your TV, everything should probably come fitted with computers. Okay. So, we have all possibilities looking at us. Now, we have talked about it. You know, the main thing to realize that computing performance has grown by about 2 million times in the last 30 years, and this last 30 years means I am talking about 1975 to 2005. Today, we have petascale computing, and we hope to arrive at a time when we would be doing great things, greater things. This is a sort of a comparison between USA and Japan. The red dots are the Japanese ones, the yellows are the USA machines, and we are right now here. This is 1 petaflop. So, we are already here. So, this open circles are the ones those are projected, but already we have reached here in 2008 we have crossed 1 petaflop rating. The Japan plans to get to 10 petaflop machines. So, this is a 10 petaflop machine, they are hoping to get it by 2011 or 2012, and as you can see that we started from here with the first supercomputer Cray-1, and then we reached in 1980 the first gigaflop machine, and then this was the teraflop, and then this is the petaflop. So, the march is on, and perils of projection, you know, you ask anyone and everyone, they will tell you that you give me this, I will deliver you this. And this is what was predicted by a scientist from NASA Ames, Dean Chapman. He wrote this paper, Computational Aerodynamics, Development and Outlook, in 1979. And I just want to draw your attention that he said that when we get this kind of number of points, so this is a million points, this is 10 million points, 100 million points. So, they said that when we reach about around 1 million points, we should be solving the flow past a complete aircraft. Now, of course, in your PC you can do it, right? You have more memory than that. How many people are computing flow past a full aircraft? Not many I know of. Of course, the companies, aircraft companies are doing it, but that does not come with this kind of projection. They work on a different issues. Well, it is probably we human beings are optimists, so we always look at the positive approach of what we can get. This you probably all know. Anything that you cannot prove, you can proclaim it as a law. So, Moore did that, and he said that every 18 months the number of processors in a chip doubles. This excludes all the supercomputers and all. Supercomputers actually outstrips Moore's law. So, there is already always an exception to Moore's law. I do not know why computer scientist people call this as Moore's law. This computer power and the memory actually are growing exponentially with time, and this memory that we are talking about, this is the RAM, not the hard disk part. Those grow actually even much faster rate, double exponential rate. And we have already said that computing power is denoted by floating point operations per second. So, that means that if you have a higher plops machine, you have higher computing power, and then we can keep on trying to speed up the performance gain of the computers, and but we must be alert to the constraints that more and more number of processors are packed in a chip. We are actually creating more heat, and that is a significant constraint. For example, by 2010 people project that there would be 1 billion transistors in a chip, and that would create about 2 kilowatts of thermal energy. And if you look at the energy density per unit area, this heat creation is more than what actually nuclear reactor does on a per unit area basis. So, it is a fascinating figure to keep back of your mind that this is a serious problem. For example, look at this ASCII-Q computer, which was housed in Los Alamos in 2002. It delivered about 30 teraflop. It had about 12,000 processors in 2048 nodes, had 12 terabytes of RAM and 600 terabytes of disk storage. This was the building that was housing this, 300,000 square feet, and it had to have those cooling towers, rows of them, and those cooling towers would reject heat into the atmosphere. And if the computer needed 3 megawatts of power, the cooling needed 2 megawatts of power. So, it's such a serious problem that you encounter. So, what happened at the time of introduction was that every time a computer is started on, it would run for a few hours, then it had to be rebooted. And we have this nice thing called mean time between failures, MTBF. So, at that time this MTBF was every few hours for ASCII-Q. Of course, in comparison today the Blue Gene of IBM that was installed in Lawrence Livermore, the power significantly came down to 2.33 megawatts, and it had a much higher power rating, you can see, as compared to 30 teraflop, this is 480 teraflop, and this is the fastest machine that we already have talked about. Okay, this is on the left is your ASCII-Q, and this is your Roadrunner of today. You can get a pretty good idea of what supercomputers look like. So, where do we go from here? Okay, the milestone set for supercomputer is to emulate the performance of a human brain. Why? Because it is still little into the future. We can continue to give excuses for some more time for not being there. What a human brain does, it performs about 10 to the power 16 synaptic events. That is equivalent to something like 10 petaflop. And human brain has only 10 terabytes of memory. So, it is worth what, 60,000 rupees now? Can you get a brain for 60,000 rupees? I do not know. The main interesting part is this, it only consumes 10 watts of power, only 10 watts of power. Now, you know your computer requires at least 100 watts to deliver 1 gigaflop. So, if you can scale up to this, you would require billion watts of power. But the interesting part is not about the speed of computing. I think it is the quality of computing that is distinctly different in human brain as compared to computer. For example, we are predicting that by 2019 we should get a exaflop machine, that is your 10 to the power 3 petaflop machine. So, next milestone, and of course, I do not know how this etymology comes about, but every time you increase it 1000-fold and you have a fancy acronym here, zetaflop, yoltaflop, zeraflop. So, it will keep coming. I think some of you can keep on thinking about putting some more numbers to the right. There it is. So, if you look at a road runner versus human brain, I told you that qualitatively human brain functions in a different way. Synaptic operations in brain are actually done through ion channels, and these are basically chemical signals. It is not electrical signal per se. You got to realize that electron travels much faster than this liquid in the ion channel under the same electric field. The bottom line is computers are faster, but they are tremendously wasteful. They are much more faster, that is why they could defeat a grandmaster, because Blue Gene L came to that stage where it could do much faster calculation, faster than a grandmaster could think of. We know that it defeated a grandmaster. Now, present day processors are manufactured on 45 nanometer scale. I think it has come down to something like 32 or something in recent document I have seen, but we are getting there, virtually hitting the wall. This hitting the wall will come about because of the heating issues, plus this is a dangerous thing lurking in the corner, indeterminacy of on off positions of switches, and this is what is called as quantum mechanics effect. So, we would not even know whether a switch is in an on state or off state. So, it has been claimed that quantum computing will take care of this. I have put a question mark because I do not believe it is as trivial as that. This paper in Nature once again state that quantum computer should be available by 2020, because there are many technical challenges, those have to be circumvented. Now, one of the reasons the heat is generated is we have too many interconnect wires, and this ohmic heating creates this heat. Suppose we replace them by optoelectronic connectors, then we can probably improvise and deliver more computing power. Okay. So, maybe future supercomputers would use laser lights for communicating data streams. People have already started working on materials like indium phosphide and RBM. They are etched on the top of silicon chip. Some references are given here. You can take a look at this if you are interested. I am not an expert, I do not know what is in store really. Well, software and algorithm played its role. I told you, starting with vector processing, we came to parallel processing. We also have to think of sometimes a new innovative architecture. This was adopted by Dr. Narendra Karmarkar at CRL Pune. that delivered us that Eka computer, which is the fastest Indian computer in the top 500 list. Today also it is in 18th spot, where he actually conceived of an innovative cluster architecture and sourced all the hardware from the market and came out with this kind of computing power. Well, parallel and cluster computing essentially involves breaking the work or a task into smaller pieces, and you do some kind of what is called as a domain decomposition used by a technique developed by a mathematician by name Schwartz. So, we call it Schwartzian domain decomposition. That is the backbone of all parallel computing, and what we do is we take the domain and break it into subdomains, and problem is solved independently in each processes. After that activity, individual processors communicate. So, this is basically the thing. We have the main problem, we split it into 4 independently, we work here at this level. After the step is done, we again go back and integrate the data for the whole domain together, and from there again we restart. So, it is basically you can realize that there is a lot of I/O involved. There is a lot of input output transactions involved. So, what happens is architecture also is built around in 2 ways. If you have a shared memory or you have a distributed memory, I am sure you all of you know of it. So, it is not really worth explaining to you what they are, but they do use some kind of special purpose software libraries like PVM, parallel virtual machine, MPIs. They are without them it is very, very difficult to work on. In fact, even I do not do myself parallel computing, I depend on my brains here. Okay, performance issues we can see is a communication is a major issue for distributed computing. If we have a poor design, we will have congestion of data and the performance deteriorates. What we do usually, we have something called a master. Under the master we have some slaves. So, this is what happens. Suppose a slave is not doing its part, then of course, the information is not sent back to the master after one step, and if all the information is not there, you cannot go to the next step. So, that is what is the problem of latency we call. So, that latency is a major issue that we need to worry about. So, we need to understand what is called as load balancing. We should give distribute the load equally, equitably among all the sub processes, so that they all conclude at the same time, send back the information to the master, so that we are ready to go for the next step. So, you also understand that between shared memory and distributed memory, shared memory will be preferred, because then from the same memory all the sub processes are tapping their information and putting them back. So, you do not have to do that much of I/O transactions as you do with a distributed memory. Okay. So, this is about massively parallel computers. What happens is, although we said that in parallel processing we will break up the problem into smaller sub pieces, but then those pieces are not completely distinct from each other. There would be some kind of overlap, because we have to communicate among the processes. So, this is what we call as overlapping subdomains, and if we have a massive parallel computing going on, this overlapping subdomains actually creates some kind of problems in communication latencies, because what one processor is doing, the conclusion of its task, it is supposed to transmit those informations near that overlapped region to its neighbors. So, if that is not done efficiently, that would also create a latency problem. So, the current trend is of course go for cluster of workstations, and then we have come to this level where we have multi-core machines, which we are seeing more and more, and then people are again relooking at shared memory systems. And as far as algorithm issues are concerned, this somewhat depends on machine architecture. Parallel algorithm development and efficient parallelizing are a subject of many such researchers. I have given you one reference here, and you can look at there are some problems which are called Nick Pippinger's class of problems which are efficiently parallelized. But this information may be dated. I am not very sure about that. There are other ways where we could contribute. We could develop better methods of calculation itself, and we have done a bit by ourselves. This or by some new implicit methods, and we get an order of magnitude improvement, and in fact that gives us a computing power improvement of the order of maybe 100 times to 1000 times. So, we end up doing lots of problems on our desktop, which probably people elsewhere use supercomputer to solve them. Okay. Now, as far as programming guidelines are concerned, I told you Fortran came in 1954, then we had all kinds of languages coming up, Algol, PL1, C, C++, Java, but Fortran is the longest surviving and very adaptable language. This adaptability actually is the key to its longevity, because it kind of incorporates all the better features of all other languages. And it is seen that Fortran actually outperforms C version of codes, because what happens in Fortran compiler, you actually can identify the kernel which is doing the main computing, and that could be hand optimized, which is not possible. And I will show you an example here. This is from a paper. Simple multiplication is done, matrix multiplication. On this side, you have the number of elements of those matrix size, and on this side is the speed. So, left hand side you are seeing Fortran, this is the C. You can see this scale is different, this is 600, this is 300. So, there is a factor difference, and what you also notice that depending on the architecture, every machine has a fair bit of plateau where it performs well, but then it has a performance degradation if the size of the problem becomes bigger than this. In this case, you can see a drastic fall, and these are 4 different machines. You can see in all of them, you can notice that Fortran always outperforms. Unfortunately, I think it is not being taught here, but all the students pick them up. It is very easy. So, when it comes to scientific computing, I am sure any of you taking up any new problem, you would be well advised to look at Fortran more seriously, because if you continue to work in scientific computing, that is the language of preference. So, I think this is a kind of a general introduction. I wanted to give it to you in this class. From the next class, we will get into the subject proper. We will talk about various aspects of scientific computing, and as I told you that I have a core of students, some of them are here. They are basically working on various aspects of our computing activities. So, any time I give you some assignments, etc., you are most welcome to visit our lab that is in the aerospace building, and you can discuss about your problem, and there are your other classmates. I can see quite a few of them. They are already use our lab, so you can also come and join them. So, this is where I stop.